So the homeworks have been graded. I'm just going to take a peek at them, and they'll be returned to you. And then there's assignment due. There was another one that will be coming. And then, you know, there will be a final project assignment that we'll talk about a little bit more later. There'll be perhaps one other sort of extra credit assignment available. Those choose to do it. All right. So the remainder of the course will really address the subject of open quantum systems. This is something that, you know, we talked about last semester in a sort of phenomenological way, and this semester we'll talk about in a more quantitative way. So what is this about, and how does it connect to things that we've sort of already been discussing? So what do we mean by an open quantum system? We have a quantum system which has some degrees of freedom associated. It's some subsystem of the universe. It could be my superconducting circuit. It could be some collection of atoms. It could be some solid state material, what have you. It's the thing that's our system. And then there's everything else that we call the environment. In a sense, this is a bipartite system of the sort that we've talked about in the context of thinking about entanglement between two subsystems. But it's more than that in the sense that we want one of these subsystems to be something which would naturally be called the environment, rather than just another subsystem to which our quantum system is coupled. What are some of the characteristics that we would say that makes this system an open system? A closed system is one where we just think about everything in the whole that's of interest is closed. That's all those degrees of freedom are the only ones that play any role in the physics. For a system to be open, there are other degrees of freedom to which our system is with which our system is interacting, which in some sense we don't have access to, or it's just too complicated to keep track of them. Okay, and so some of the phenomenology we have here is that, you know, if we think about the closed system versus the open system, if we have a closed system, then energy is conserved. And if we have an open system, energy need not be conserved. In particular, we can have dissipation. We can have energy that is lost. Of course, we can also have amplification. That's another way our system we might think about having open, but let's just, for the moment, restrict ourselves to thinking about dissipation. Well, if we have a closed system, then what we have is reversible dynamics. As I say, we have a Hamiltonian. And if we have a Hamiltonian, then in principle, we can just reverse time by just taking the Hamiltonian to minus the Hamiltonian. And a system that involves, according to the minus the Hamiltonian, is equivalent to a system evolving with the Hamiltonian, but going the other way in time. This is true whether I'm talking about quantum mechanics or whether I'm talking about classical dynamics. we have reversible dynamics. In principle, we have a trajectory moving through phase space. In principle, we can reverse it and take it back to the initial point in phase space. Whereas in an open quantum system, we can look at dynamics that we recall irreversible, meaning that given the state of the system at some time, we can't take it backwards in time. Again, these two things, these things are true whether we're talking about classical dynamics or quantum dynamics. We have these kinds of phenomenology. For the specific case, for classical systems, in this case, we would say that we have, Hamiltonian and quantumly, that Hamiltonian we would say is unitary, right? The time evolution is unitary. Whereas for an open system, we can think about evolution that is non-unitary. Moreover, in a closed quantum system, we have information is not lost. All the information's there in the closed system, and that's equivalent to saying that the entropy is unchanged. Whereas in this kind of system, we can have information loss. And entropy can increase. Because what is entropy other than a description of the information I don't have? The entropy, Boltzmann expression from entropy is just another form of Shannon information, and Shannon information tells me something about the information I'm missing that if I learned, I get something new. So where is the information going? Well, it's going from one system into the other, and I've just lost it. I've lost it a lot of different ways, but that's one of the ways I could lose it. Now, there's an important aspect of this that is sort of uniquely quantum, which is not just that all these things are common between quantum and classical physics, but there are some particularly important aspects that are uniquely quantum. For the open quantum system. And the way in which information is lost in quantum mechanics can mean that quantum coherence is lost. The ability for the system to exhibit interference between alternatives, that is lost, and that loss of coherence is what we call decoherence. Decoherence is a very important physical phenomenon. It's not an interpretation of quantum mechanics, it's part of quantum mechanics. It is a way that it comes out of the quantum theory. And we need to understand that, how coherence is lost through open quantum system dynamics. And there's another sort of maybe uniquely quantum, but maybe not, which is intimately also related to information loss, is also about information gain. And that's about measurement. Now, obviously, measurement is kind of one of those hot potatoes when thinking about quantum mechanics. And do you want to touch that potato? But really, there's an important connection here between open quantum system dynamics and the whole question of quantum measurement. Because when we are doing a quantum measurement, what are we doing? We have some quantum system which is coupled to a meter. The meter itself is a physical thing, and if we're going to ever get hope of answering at least some aspects of thinking about the quantum measurement, we need to understand the quantum description of how information is taken from the quantum system to the meter so that, in principle, we could read it out. And in a way that we might call a measurement, as opposed to any other old bipartite dynamics. I mean, the thing for me, I remember when I first learned quantum mechanics, and maybe you had this experience as well, I'm willing to accept that, you know, there's something special that's different about when a measurement happens compared to something else, if you could define to me what a measurement is. And if a measurement is, if the meter, the thing that's doing the measurement, is sort of outside of quantum mechanics itself, how do I know when that thing qualifies to be given that special status of outside of the physical theory? I mean, that's what Bohr kind of scrambled up in talking about the classical meter. But we'll see some aspects of that explained through the foundational theory of open quantum systems. We obviously we won't be able to answer the whole problem, otherwise, you know, I'd be in Sweden, or, you know, someday I'd be in Sweden. All right.
So I have a question.
Yes, I'm listening.
Okay, so you have two entangled photons. If you measure one, then you know the other one's going to be correlated. If you don't measure this one, or this one's destroyed, you never measure it. This one's kind of floating out here.
Yeah, well, we can talk more about, I mean, I think what's important in understanding quantum mechanics altogether is the difference between what is and what we know. Okay? So, you know, if I have this cap in my hand, you know, you don't know which hand it's in, but so you would assign a 50-50 probability to it. Your state assignment is a 50-50 chance of one or the other. When you see it, now it's here and you know for sure. And in a similar spirit, in a quantum measurement, a state is really our description of what we know about the system, not what is in the world. Okay? And that's part of the problem, is the whole notion of when we learn something, what did we learn if we didn't learn what was already there to begin with? And the degree to which our measurement action made something, you know, that's, yeah, I'm not going to defend that. We got work to do.
So
we got work to do.
Okay.
Yeah.
And decoherence, is that optical coherence, or
Well, we'll talk about it.
Dephasing?
So decoherence is a process, a physical process by which coherence is lost. And we'll talk about how that happens. We'll talk about it. Okay, so, right. So, you know, example that we've already seen of the difference between this kind of closed and open system in thinking about quantum optics as an example, and that has these some of these features that we've already looked at, is, for example, the idea of, let's suppose I have a two-level atom and it's in the excited state. Okay? Now, we can think about the process of spontaneous emission. Right? So, in this case, we could say, all right, why is this system spontaneously emit? you know, in the absence of anything else, the excited state is a stationary state of the Hamiltonian of the atom. As I say, it's an eigenstate of the Hamiltonian, which makes it a so-called stationary state. To be stationary means it doesn't change. But we know that what happens is this thing will decay to the ground state with some rate. And we know the problem, if we start the system in the excited state, it doesn't stay there. And the reason is because the atom, which is our system, is coupled to the electromagnetic vacuum or field. And there could be also stimulated emission if there's some black body photons that are at that frequency. They could stimulate the thing a bit. But let's just say that it's in the vacuum, so that the joint system of the atom and the field initially was the atom in the excited state and the field in the vacuum, right? So my initial state is this, and what we know at a later time, the probability to be in the excited state just decays exponentially. And the state at a later time, this is at time equals 0, excuse me, at a later time, I'll have less probability in the, and I'll have one photon in some mode that's propagating away, and the atom will be in the ground state, right? This state is a mixed state. I've lost information, it's no longer a pure state. Ultimately, actually, it goes at infinite time, it goes to the ground state, it's a pure state. Again, that's a kind of special kind of channel of decay, but that's sort of neither here nor there for the moment. The main point I want to emphasize here is two things. One is we have energy dissipation, energy lost from the atom. And we have irreversible. In fact, we would lose coherence as well if I started a superposition of the ground and excited at some initial time, and at a later time, I have no idea, this coherence is lost. There's no longer a superposition. So there's decoherence that happens along the way. This is in contrast to the James Cummings model. That we've studied this semester. What did we study last semester? God, oh, we're still studying the things you got time. Anyway, where we imagine a atom coupled to a single mode of the electromagnetic field, in which case, with that same initial condition, we know that at a later time, we get Rabi oscillations, so-called vacuum Rabi oscillations. And the total state of the system we typically would write as a pure state. Maybe it depends on the choice of Hamilton, but something like this, where G is the coupling constant that couples the quantized field to the atom, right? It's the vacuum Rabi frequency, as we've called it in the past. So what do we notice about this evolution? Firstly, energy is flowing from the atom to the field, but it's also flowing back from the field to the atom in an oscillatory way. Energy flows to and fro. Fro, I don't know how you spell fro. Just fro like that? Okay, thank you. Reversible oscillation. Information is also flowing between the two at some intermediate time as you're studying in your homework. This atom and the field become entangled with one another, right? So there is entanglement between the atom and the field. We expect that because the atom and field are interacting with one another, and any two subsystems that interact with one another will become entangled with one another if one of them is in a pure state, say. They're both in a pure state. But the entanglement goes away, it becomes entangled and then becomes unentangled, and then it becomes entangled again, and it's going back and forth in this reversible oscillation. So this is closed, and this is open. Why? What physically is going on here differently? I mean, they're both the case where the atom is coupled to the field. But why in this case is the nature of the dynamics so different in that the system is having this unitary evolution which is perfectly reversible? At any time I can take this initial state and map it back to that state, unique with just doing the time reverse of the Hamiltonian. Why physically does this system undergo this kind of dynamics, whereas this one, where I had the atom in free space, undergo this kind of irreversible dynamics, where here the probability to be in the excited state at some time t, the thing in the, is, cosine squared, which is reversible.
Was the lossless cavity.
Right. This guy is lossless. So of course this is really just an approximation. We know that really every closed system is in fact a little bit open. There might be decay out here, and I also might spontaneously emit it out of the cavity, right? So the strong coupling that we've talked about was a situation where G was huge compared to gamma and kappa, in which case we could have lots of coherence before the coherence is lost. But why mathematically maybe they're both described by an atom with electric dipole moment coupled to the field. There's a Hamiltonian, d dot e. It evolves according to time. Why does this one undergo this kind of evolution, whereas this one has this? What's different about them? They're both the field coupled to the atom. why does the existence of this cavity, which let's assume is really quite good,
Is it because here we know exactly the mode the photon is produced, and here it's like it can go into any.
right. So there's something quite different here about when I call this 0, this is 0 for all modes. And Harry's point here is important, is that in the atom in free space, this is coupled to a continuum of modes. An uncountably infinite number of modes. Whereas in this case, this is a single mode. This is 1 degree of freedom. And really it's a coupling, this is more like coupled oscillators. Whereas I could think about this system as also the atom is a two-level system, kind of an oscillator, but it's coupled to a continuum of oscillators. So, importantly, this can only be approximately true. Because the fundamental underlying theory is Hamiltonians, unitary evolution, reversible, but in the same way that the Hamiltonian dynamics that we have in classical dynamics is a kind of fundamental theory, we can still have friction in Newton's equations, even though Newton's equations don't really allow for friction. Friction's an effective theory, that's a good approximation. So to get this is gonna, we've already kind of seen it, and we don't maybe remember it, but we did the Wigner-Weisskopf approximation, and man, that's ugly and a pain in the butt to do. And you stand on one foot as much as you can and wave your hands to show how you can separate this time scale and something's Markovian. We're gonna do it again to remind ourselves of all of those things. But what's critical for something to be an open system in this context, and the context of reversibility, is that the environment has to have a large, approaching uncountably infinite number of degrees of freedom, so that the system, once the energy or information goes into the environment, it's gone. In this case, what happens is the photon flies away. Now, you put some mirrors and bounce it back, with the big parallel pillar, maybe you can get the energy back. But basically, that's what's happening here. Okay, so we're going to get to that, the whole question of how we can see this approximate evolution. But before we get there, there's just sort of some foundational descriptions that are quite useful from both the mathematical point of view and then in understanding the physics of what's going on. Yeah, I'm listening.
So I have a stupid question. So when you have the spontaneous emission, right? So you have the energy level goes from the excited state to ground state. So I know the energy of the photon, which means the way I'm thinking, there must be only 2 modes, right? Associated with the polarization of the photon because the energy is fixed.
Okay, so there are a few things I would say. First is the energy is not for sure definite because it's more like a photon wave packet, but that's not the most important point. The most important point is the direction in which the photon, so the photon has both, remember what's a mode, the typical modes we would think about are plane wave modes with a certain polarization. Where this might represent the 2 polarization states, but what's really important is K. So the atom is, when the atom say this transition is a pi transition, means the dipole is oscillating along some direction. The photon can be emitted in any direction with a certain weighting depending on the dipole. And it's the continuum of directions of propagation that matter. Now, what that means also is, in terms of time, this is something we didn't really talk about in great detail, but we can solve this in the Wigner-Weisskopf relation. What we have is a spherical wave that has a different amplitude, and it has it's kind of a wave packet that has a wavefront and an extent that depends on the time evolution. So what happens is I have a packet that I can't see anything before a certain time, but after that there's a certain probability of amplitude. So what I really have is a wave packet that's propagating out spherically that has a kind of temporal width, which is about the lifetime of the atom. It's not really a photon that has a definite energy.
Doesn't the direction depend on the dipole?
It does.
Yeah.
I mean, so if it's the dipole's oscillating that, it's most likely to be here, but it could go in other directions as well. All right, it's a good piece of physics. Right. So I want to talk about because this will give us some foundational mathematics to understand the physics as well, the theory of quantum channels. Okay, so what do I mean by this? A quantum channel is an input-output relation of a quantum state. So we'd say the output quantum state is some channel acting on the input state. It's a generalization of time evolution that we might have say that's unitary time evolution. That would tell me how the state is evolved from the input to the output. Okay. Now we can write this down in a kind of very general way. So let's suppose that at time t=0, we have some joint state of the system and the environment, okay? So I'm assuming I have a system and I have an environment. And I have some initial state at time t=0. And I want to know what is the state of the system alone after these guys evolve together. The system from the environment is the universe, okay? Everything that's not the system, I'm calling the rest of the universe, I'm calling the environment. And so the universe, to the degree to which there are no other degrees of freedom, means that everything evolves according to some unitary time dynamics. So this is the closed quantum system dynamics of everything. It's kind of now correct, devoid of a lot of meaning, but this is just the facts, right? And if I wanted to know what is the state of the system alone, independent of the environment, after they have interacted, how would I find that? I trace out the environment. Okay, so this is fine. Of particular interest is the case that at the initial time, the system and the environment are uncorrelated, okay? Because that's the situation in which I can talk about something about what happens to the state of the system without having it be something that is part of the composite. Okay, so I'm assuming at the initial time, the system and environment are uncorrelated, and then I'm gonna let them evolve together, okay? Moreover, I'm gonna look at an even more specific case, which seems kind of nuts, but let's just say it. And suppose that the state of the environment at the initial time is pure. I'm going to call that initial state 0. Sometimes called the fiducial state.
You said the system are correlated, you mean the system and the environment are uncorrelated?
Are uncorrelated. This, system and environment. Excuse me. At the initial time. At a later time, they will become correlated, generally speaking, due to the interaction between the system and the environment. They'll interact and they'll become correlated, and in fact, they'll become entangled with one another. Now, I want to ask, this seems a little nuts because the environment is supposed to be this mass of uncountably infinite numbers of degrees of freedom, and it's the environment, for God's sakes. We know almost nothing about it. To call it a pure state means we know absolutely everything about it, so why in the world would we make this choice? Well, there's kind of two reasons. One is it can be a situation of interest. For example, it might be the case that at the energy scales of interest of the system, the environment is at such low temperature that there's almost no thermal noise in the environment. So for example, in our optics problem, when we thought about a two-level atom and we're thinking about optical photons, there's no photons unless we had the at those narrow frequencies. In the narrow band of interest, it might be the case that there's just no excitations around it. To some degree, I can just call it the system in its ground state, the environment in its ground state, like the vacuum. There's another reason, which is more mathematical, to see that the kinds of ways we define quantum channels, it's convenient to take the environment as being a pure state because we don't actually get anything more general in terms of our description of the quantum channel by choosing the environment to be mixed. So it's just kind of a convenience mathematically, but physically it's not irrelevant, okay?
That is related to this Nymarkization, right? Where you can always expand your Hilbert space.
That's right, yeah. Okay, so if we plug that in to this thing, then what we see, well, let me go to a fresh board. So what this says with this condition is that if at t equals 0, the joint state of the system and the environment was there's some initial state of the system and the environment is in the fiducial pure state. At a later time, the state of the system is I trace out the environment and I evolve the joint that way. You with me? Right? So the trace over the environment is the sum of the diagonal matrix elements of the matrix with respect to a basis of states for the environment. So I can think about a set of states I'll call mu, which is some basis for the Hilbert space of the environment. In which case I can write this trace as the sum of the diagonal matrix elements Now, this is a little bit confusing, but I can look at this, notice that this guy, the unitary here, is something which is coupling the system and environment together, okay? These states are only states of the environment. They're not states that have anything to do with the system at all. But I can rearrange this partial trace in the following way. Where I've kind of moved this doesn't really act on the state. This is what we call a partial matrix element. It's not a number because this thing acted on both the system and environment. And I'm taking the matrix element only in respect to part of this subsystem, the environment. So this thing here is not a number. It's an operator. It's an operator that acts on the system. I'm going to call that operator M. And this is its dagger. And so we get a very important equation here, a really important equation that really we should have all learned long ago if we didn't learn it yet. Which is that in this kind of dynamics, where we have a system and another ancillary subsystem coupled together over some amount of time, and then I look at the state of one, I can write the state, the output state, as this equation. Where the MUs are given by the partial matrix element of the unitary that couples them together, and they're called the Krauss operators. Or I prefer to call them the measurement operators, which I like to call them M, because they're very much intimately related to the process of quantum measurement. And this channel is known as a Krauss map. This is really important. It's a piece of fundamental quantum mechanics that everyone needs to learn. What's different about this than closed quantum system dynamics? The closed quantum system dynamics, the unitary dynamics, was that the system evolved according to some system unitary. This looks kind of like that, but it's not really the same thing because I have this sum over all these different mu's. The m's are not necessarily, and mostly not, unitary. Well, I'll give you an example where it is a unitary in a moment. But importantly, these operators are not unitary operators. But they tell me the input-output. They tell me how to take the state of the system at the initial time and evolve it to the state at a later time due to as the system interacts with the environment. And the Krauss map is not unitary evolution, or not necessarily. I mean, the unitary evolution is one example. That's where only have one and only one Krauss operator. So this goes beyond unitary evolution. So it's always going to be the case that when I have two subsystems that couple together and I look at one on its own, its evolution is not unitary. It's really not about the system being open so much in the sense of the uncountably infinite degrees of freedom, because this said nothing about how big the environment was relative to the system, how many degrees of freedom, or anything reversible versus irreversible. It's just saying that if I have two things that are coupled together and they become entangled in this way, when I trace out the environment, I've lost information, and that means that I get non-unitary evolution. This is one of the things we discuss as one of the hallmarks of entanglement, is that when I have entanglement, if I look at one piece of it, it becomes mixed. Okay, and let's look at that a little bit more closely here. Maybe I should say, if for the special case that the joint evolution was separable, so if my evolution acted separately on the system and the environment, and there was no coupling between the system and environment, and I did the same rigmarole, what would the Krauss map be? I would find that M is equal to this. There's only one, and my time evolution would be M and dagger, which is unitary evolution. So if they don't couple together, then we have just unitary evolution for the system alone. But when they couple together, I don't have a single unitary, I have Krauss operators, and my map looks like that. Okay. Let's probe that a little bit more closely, okay? Try to understand what the heck is going on, what these Krauss operators mean, and what this is telling me. So let's look at what's called the unitary representation of the channel. So let's see how this thing acts on, so let the joint state of the system and the environment at the initial time be some pure state of the system and the fiducial state of the environment. It's just a specific example, okay? We could have had the state of the system be a mixed state. Now I'm taking the state of the system to be a pure state. If I now ask this guy, I want to know what is the joint state of the system and the environment at a later time. Well, I evolve joint thing unitarily. But if I insert a complete set of, I multiply this by the identity acting on both guys, that's the identity on the system and the identity on the environment. And I write this in terms of the basis that some particular, any old basis that I'm labeling by mu, then what do I get? I have to sum over mu. What I get in that case is the partial matrix element of this, so I'm going to get mu acting on the state of the system let's take a look at that. This is saying I started with this product state. The system was in some pure state. The environment was in the fiducial state. I then let them interact through this entangling interaction. I just gave it away. It's an entangling interaction. This is an entangled state. The system and the environment have become entangled through their mutual interaction. That's always going to be the case. If you have two systems that interact with one another and the joint state of the system started pure, then at a later time they will become correlated. And if they're correlated, the only way they can be correlated is they're entangled. There's no other kind of correlation for pure states except for entanglement. That's all there is.
This kind of reminds me of the Van Sitters energy theorem, but that's purely optical.
Well, you know, a lot of things are very close because it's linear algebra in the end. It's just there could be some relations there. But let's take a closer look at this entangled state. Firstly, I want to mention that the ends are not unitary. which means that this state is not a normalized state, because only unitary operators preserve the norm. Okay? So, if I want to ask what is the norm squared of this guy, that's equal to this. It's a positive number, right? And it's a number that's less than 1, because, well, let's explain. So I'm going to call this number very suggestively P. It's a positive number. Let's look at the sum of those P's. This is the sum of mu dagger mu's. Let's write what that is. Remember that the mu's are the partial matrix elements. There they are. The sum of this sum is equal to the sum of m dagger, which is U0 right? That's m dagger, that's m. Sum over mu. When I sum over mu, that's the identity. U dagger U is the identity. This is a normalized state. This equals 1. So an important fact here is that the sum over mu of mu dagger mu is the identity. It's a generalization of what we had for unitary dagger. If this was a single unitary, U dagger U is the identity. But not a single one of them sums to identity. The sum of all the mu daggers mu sum to the identity. Which means this P's are a probability. What probability is it? In other words, they're positive numbers and they sum to 1. It's a normalized probability distribution. Let me rewrite this joint state thus as sum over mu, the square root of P mu, where I'm writing this is defined to be the action of the Krauss operator on the state and then renormalized. Okay. The magnitude of this is the square root of P mu, because the magnitude squared is P mu. Okay, so let's look at this carefully. We started the state as a product state. We evolved according to this interaction, which entangled the system and the environment in this way, such that I correlate for every possible state of the environment, there is an action of mu on the state. That particular, if we renormalize it, it looks like this. Now, I ask you the following question. is this the Schmidt decomposition of the entangled state? Sure. Looks like it, right? It's a sum over one index, and it's not a sum over two index, and I have the, what looks like the Schmidt coefficients there. Trick question. It really looks like the Schmidt decomposition, but it isn't, because these are not necessarily orthogonal.
And this isn't necessarily unique space.
That's right. But you could see that, I mean, if these guys were orthogonal, it is a Schmidt decomposition, but because these guys aren't unitary, these aren't orthogonal. But it is an entangled state. So now I ask you the following question. If I ask, what is the state of the system alone, getting rid of the environment at a later time, that's the trace of the environment of the joint state. Which is equal to the trace of the environment where I take this outer product with that. Let's just do it because what the heck. So what happens when I take the trace over the environment? Well, I get a delta mu mu prime, and this becomes the sum over because these guys were a basis, so that's orthogonal states of the environment. So, our quantum channel took this initial pure state of the system to a mixed state. This state is a statistical mixture of these phi mu's weighted by this probability distribution, where the phi mu's are the action of the Krauss operator on the state renormalized, and the probability in the sum is given by this rule. So what we learned here is that the quantum channel generally takes a pure state to a mixed state. This is non-unitary. Unitary evolution preserves the purity, but the open quantum system can change the purity. It can particularly reduce the purity, make the system more mixed because the information is lost. The way we understand it is that the system becomes entangled with the environment. implies the system becomes mixed. Because as we've discussed, if you have a joint system which is entangled, the subsystem will be mixed. And we see that here. We also see that we have a statistical mixture. Not system, but statistical. With an ensemble decomposition, we have a mixture of pure states with some probability where the p mu's are given by this rule, and the psi mu's are given by this rule.
So this all assumes that the environment's a pure state.
It does. I mean, if the environment is not in an initial, what's critical here, what's required, is that at the initial time, the system and the environment are uncorrelated. If the environment were not in a pure state to begin with, the same thing would carry on, but we'd have to have more sums, because we can write the environment itself as its own statistical mixture of pure states, and everything would follow through essentially the same. That's why we don't bother with that mathematically. But what's critical to this formalism is that at the initial time, the system and the environment are uncorrelated with one another. And then at the later time, they do become correlated. What can we say about, so this is equivalent to the Krauss map, which says that the output state is related to the input state, where the sum over mu dagger mu is the identity on the system. This kind of quantum channel, which I might write as script E, don't call it epsilon, it drives me nuts. It's an E for it. What can we say about the properties of this? So this kind of quantum map, or quantum channel, firstly, we immediately see that the output state is certainly Hermitian, because the input state was. And moreover, because this came from tracing out the joint system and environment, it must be the case that this is a physical state with positive eigenvalues. It's meaning this is the output state is a physical state, because we obtained it through a physical process. We started with a joint system, we evolved them, we traced it out, and so it preserves positivity. If it's going to be a physical state, the eigenvalues of the density matrix can't be negative. The other thing we can see is that what's the trace of the output state? Well, that's equal to the trace of mu and row and dagger. But the trace we can rearrange because in the trace I can do cyclic permutations. And this is the identity. So this is equal to the trace. So this map is also trace preserving. So a Krauss map preserves positivity and, as written, also preserves the trace. These kinds of maps are a little even more, I don't want to get into the details because it's kind of complicated. This has a more technical notion of what's known as completely positive. What makes it not just positive, completely positive? Well, that's a story for another time. But often these are called completely positive trace preserving maps, a CPTP. The TP part is actually not required for it to be physical. We can look at maps that we only look at a subspace of the system and not the whole system, and not preserve the trace, and then we would just call it a CP map. But, right. Let me see, what else did I want to say before we get into the whole business of the measurement model? Oh yeah, maybe I'll say one other thing, and that'll be a good place for us to stop.
Sorry, what was the CP stand for?
Oh, good, thank you. Completely positive.
Oh, okay.
The term completely positive is kind of heavy-handed here. You don't really, it's more important that it preserves the positivity. The fact that it's completely positive is just, it's a whole nother story that's not so important for our purposes here. But I just mention it because it's a jargon you'll hear people say all the time. We'll talk about a CP map. What is true is that every CP map is a Krauss map, and every Krauss map is a CP map. And every Krauss map can be understood as through a unitary entangling interaction between the system and the environment. This is the worst possible. Where's my rag? Oh, there it is. Okay, so the last thing I wanted to mention about these CP maps so what we have is at the output state, there's a CP map on the input state, which we wrote in terms of a Krauss decomposition. Right? What I wanted to just mention is that this set of Krauss operators is not unique. This is really important, and we're going to talk about it more over. So what is that? Why is that true? Well, remember how we obtained this in the first place. What we did is we said that we traced over the environment of the joint system and environment unitarily evolved. That's what we had. We said that this, we got this from this, right? Where the hell did mu come from? We just picked a basis. Who said what basis it was? I could have chosen any basis for the environment, and I'd get the same thing. So this also equals some other set of Krauss operators where these guys are just, for example, some unitary matrix that connects two bases. So if I have another basis mu, which is another basis for environment, that's elements of a unitary matrix, and I can do a unitary remixing of the Krauss operators, and that's these give me the same map. It's an example of the fact we remember that when I said somewhere, let's see, the ensemble decomposition. Yeah. The ensemble decomposition is not unique. There are many different ensembles that give me the same mixed state. I could write this as a sum over nu, q mu, phi mu, phi mu. That would give me the same mixed state, because I'm not keeping track of the environment. What that would correspond to is, I could rewrite this guy both of these are the same state. They're correlated differently to the environment, but in the same way that I can think about a singlet as being spin up along x correlated to spin down along x, I can also think about it as spin up along a z correlates. I don't know which correlate, there's many different correlations which would add it up, give me the same overall pure state, and when I trace, since I'm tracing out the environment, the thing that I get can't depend on that. So the set of Krauss operators is not unique. But the overall sum gives me the same overall state. All right, we will